In derivatives number 8, we're going to start talking about motion, and we'll continue this discussion in number 9. It's a pretty big topic for us. And specifically, we're talking about what's called rectilinear motion. And all that means is we have a number line like this, like an X number line, a one-dimensional number line. And we have a particle on this number line. And all that guy is doing is moving right and left and right and left. Sometimes that straight line might be positioned vertically. And in that case, your object would be just moving up and down. Our main goal for today is just to look at the relationship between position, velocity, and acceleration. So position, common names of the function would be x of t or s of t. And just be careful with this notation here. You're used to seeing this x as being the independent variable written inside the parentheses, but we've switched its place. The name of the function is x, and that is because we are just on an x number line and we're moving left and right. And t is our independent variable. And what that function does is it tells you where an object is after t, seconds, minutes, hours, days, whatever your unit of time happens to be. So let's just say that our position function is this one here. If I wanted to know where on this x number line that particle was after, say, 2 seconds, then I would just plug in a 2 in for my t. So I'd put a 2 where I see those t's. And when I do that, I get -6 as my answer. And the way I interpret that is on this x number line up here, after 2 seconds of travel, my particle is at a position of -6 on that number line at t equals 2. The velocity of an object is commonly called v of t, and that is the instantaneous rate of change of position. That's how fast the particle's position is changing at an instant. And we also said that an instantaneous rate of change is a derivative. So to find the velocity, we're just going to do the derivative of my x function. For instance, on this x of t, my velocity function would be 2t minus 5. And at any time t I plugged in, that would tell me what the velocity was at that moment in time. Next up is acceleration. And acceleration is commonly called a. And that is our instantaneous rate of change of the velocity. That's how fast the velocity is changing at a given moment in time. And again, this is an instantaneous rate of change, which we know as a derivative. So to find our acceleration, we're just going to do the derivative of our function v. If you want to relate that all the way back to position, it would be the second derivative of position. So a little bit about how to interpret that velocity. If your velocity value is 0, what that means is that your object is not moving. Another way to say that is that your object is at rest. And if your velocity is positive, so if v of t is greater than 0, that's just another way of saying v of t is positive. That means that your object is moving in a positive direction. So if we're on that x number line, a positive direction is going to be to the right. So our object would be moving to the right. If you happen to be in the context of an up and down motion, then you would be moving up. And if your velocity is less than 0, that just means your velocity is negative. And again, on that number line, if you have a negative velocity, what that means is that your particle is moving to the left. And if you happen to be in an up and down movement, then that means that your object would be moving in a downward direction. So just in any negative direction. And for acceleration, if your acceleration is equal to 0, that means that you're on cruise control. You're neither speeding up nor slowing down. So we would say that your velocity is constant. If your acceleration is positive, that means your foot is on the gas pedal and your velocity is increasing. And if your acceleration is less than 0, that means your velocity is decreasing. It's also important to know what units belong with each one of these. Sometimes you'll be asked to give units, but sometimes the units will give you some insight into how to solve a problem. So a position unit is just linear. So that would be just centimeters, feet, kilometers, yards, miles, any of those. Just something that you would measure as a distance. When you have a velocity, since it's a rate of change, those are a rate unit. So some sample rate is meters per second. So it's how far, how much of something over some time unit. So there's some sample rates for you. Meters per second is a popular one, feet per minute, miles per hour. And acceleration is the rate of the rate. So that tells you how fast velocity is changing. So it would be something like meters per second for each second. And I'm going to play with this meters per second algebraically here for a quick second. So I can rewrite this as meters per second divided by seconds, which I've done right here. And I'm just going to treat this division as multiplying by the reciprocal. And you get that acceleration unit is meters per second squared. And this is a common way to express an acceleration. And it really is just that one, just rewritten a little bit differently. And since they mean the same thing, the choice is yours in how you choose to write it. When you look at it like this, it just kind of gets to the heart of what an acceleration is. It's how that velocity is changing over time. And our last item here is speed. And you can just think of a speedometer in your car. It's always a positive reading, whether you're going forward or backward. So think of speed as being the absolute value of that velocity. So it doesn't matter if you're moving to the right or to the left, that speed will always be a non-negative number. And then just some important things to note, especially when we get to word problems and applications of derivatives. When you see a rate, then know that a derivative has already been taken. So you are already sitting at a derivative. And the other important thing to note is when an object changes direction, what that means is that your velocity equals 0 and undergoes a sign change. So if my velocity goes from a positive value to a negative value, that means I'm going from a rightward movement to a leftward movement, and that indicates a change in direction. And in order to get from a positive to a negative, you have to bypass that 0. That's the good old IVT showing up for us. And it works the other way around too. If we go from a negative velocity to a positive velocity, that means I'm going from a leftward movement to a rightward movement, which is a change in direction. And again, if you're going from a negative velocity to a positive, you have to bypass that 0 in order to get there. So an example problem here that just shows you how we're going to use all this information. So in this graph, I have y equals v of t. So I am looking at a velocity graph. So it's important for you to realize that this is not the particle itself that's going down and bouncing and coming up and going down. This just tells me what the velocity of that particle is. Your object is actually just on an x number line that's not even in this velocity graph. This velocity graph just tells you how that particle is moving on that number line. So the fact that my velocity begins at a 4, that means that my particle, wherever it starts, is going to begin with a rightward movement. So this indicates, because my velocity is positive, this indicates my particle is moving to the right until t equals 2. And then at t equals 2, it changes direction, and now it's going to move left all along this interval. At t equals 5, it stops momentarily, but then continues in a leftward motion. So in this first question, it wants to know when is the object at rest. And I know that an object is at rest when that velocity equals 0. And I can look at my velocity graph and I see that happens in 3 places. So here at 2, here at 5, and here at 7. And my reason is because velocity equals 0. So this justification part is accomplished right here. I just say what it is about this velocity graph that made me pick those values. Question 2 is asking where the object changes direction. And there's a little higher requirement to a change in direction. It starts where the velocity equals 0, but I also need to undergo a sign change indicating I'm going from a right to a left movement or from a left to a right. So of these resting places that I found in part A, the only ones that indicate a change in direction is this one at 2, because that's the only time my velocity goes from a positive to a negative. So I just say t equals 2, and then I say my reason for picking that one. It's because my velocity equals 0, and I did a sign change. My next question wants to know on what time interval. So now I have an interval of time, not a moment in time like the previous two. And I want my object to be moving to the right. And I know an object moves to the right where my velocity is positive. Here's my velocity graph, and I know this is positive at all points above the x-axis. So my interval is going to go from 0 to 2. And notice how I put a bracket on the endpoint, and at 2, I actually said the velocity equals 0 at 2, so I needed to put a parenthesis, so I'm not including 2 as a rightward movement because my particle is actually stopped at 2. And as far as my justification, I just say what it is about this velocity graph that made me pick this interval, and it was the fact that velocity was greater than 0. The next question is a leftward movement, so where does the object move to the left? And I know that's going to happen when my velocity graph is less than 0. So all these places below the x-axis is what I'm going to go for right here. And actually at the 5 and the 7, I'm actually equal to 0, so I don't want to include those. So my intervals are from 2 to 5, and then I pick up after the 5 and go to 7. And again, the way I don't include those points on the x-axis is by putting parentheses on my intervals. Part E wants to know where the acceleration is positive. And I know acceleration is the derivative of velocity. And when I say derivative, just think slope. So I want to know where the slope of v is positive. So as I look, this is a negative slope. So my positive slope is happening right here and right here. So my intervals are going to go from 3 to 5 and from 6 to 7. And my reason for choosing these was just because v of t is increasing. And my last question here wants to know where the acceleration of the object is negative. And again, just think of acceleration as the derivative of velocity. And when I say derivative, just think slope. So I want to know where the slope of my velocity graph is negative, and that is happening on this red portion all the way here, and then negative again from 5 to 6. So my intervals are going to go from the 0 to the 3 and from 5 to 6. And my reason for choosing those intervals was that is where this v of t graph is decreasing. So one thing I want to call your attention to on all of my answers up here, notice that on every single one of these answers, I have referenced v of t. So every one of my answers, I reference v of t here and here. And that is because that is what I'm given to work with. So whatever information you're given is what you want to use as your reasoning in choosing your answer. The next thing we're going to talk about is the difference between displacement and total distance traveled. Displacement just refers to an object's change in position. So from its initial position to its ending position, how much did it change? And I've twisted this formula around a little bit. So if you take your end minus your initial, you get your displacement. But if I add this initial position to both sides, I get my ending position is initial plus displacement. This will have a purpose for us later on in a month or two, but for right now, just know it exists. My total distance traveled is exactly that. It is all my movements added together. So the sum of all the movements of an object, and it doesn't matter which direction you're going. So over here, just so you could see the difference between the two, I have an object that's moving from point A. So it starts at A, and it goes to B, to C, to D, to E, to F, and it ends up at F. If I wanted the displacement of this object, so my displacement would be that direct line distance from the ending to the beginning. So that would be the displacement of my object. And I would just do like a simple Pythagorean theorem to find what it is, but whatever that distance is. If I wanted the total distance traveled, then I would track all the movements. So I would take this movement plus this one, plus this one, plus this one, and I would literally add all those movements together. So just a little example of displacement versus total distance traveled. So I have an object that starts at x equals 2 on my number line, and then I'm given some movements right here. So my object starts at a 2, and it's going to move to the right 5. So I'm going to move to the right 5, and it's going to end up being at 7. And then I'm going to move to the left 3. So 1, 2, 3, and I'm going to be at the 4. And then I'm going to move to the right 2, 1, 2, and I'm going to be at the 6. So I started here, and I ended here. So my displacement is just going to be the end minus my initial. So my ending position is the 6. My initial position is the 2. So my displacement is just 6 minus 2, or 4. And you can see that's just the difference between these 2 points. So 1, 2, 3, 4. Another way you can get that displacement is just to add all your movements together. So I could go right 5, so positive 5, a negative 3, and a positive 2. And you can see when I do those calculations, I could get that 4 that way as well. My end position is just that 6. And I can see that's the answer because I tracked out the movements. But you could use this little formula up here, and you could say that all I have to do is take my initial position, which was the 2, add my displacement, which was the 4, and I could arrive at the 6 that way as well. My total distance traveled is this, except for I'm going to take everything positive. So I'm going to take the 5 plus the 3 plus the 2. I look at all the movements and I pay no attention to whether I move into the right or to the left, and I add all that together and I get my total distance traveled is going to be 10. Our last example is more analytical in nature. We don't have a graph for this. All we're given is a position equation. So here's my position equation. And first I'm asked to find what the velocity is at t equals 5. So I first find my velocity equation by doing the derivative of position. And once I write down what my velocity equation is, I now evaluate it for a t value of 5. So now I'm going to plug in a 5 for all my t's. And I get my velocity at t equals 5 is 8 meters per second. So I went ahead and put a velocity unit on that because I know my distance is measured in meters and my time is in seconds. The next question wants acceleration, and I know that is the derivative of velocity, so I first write my acceleration function. So my acceleration function is just the derivative of this velocity function, so just power rule is 2t minus 4, and now I evaluate it for a t value of 5, so I'm going to plug a 5 into that function. So here's my acceleration function, and here is my acceleration at t equals 5, and I get a 6 meters per second squared. My next question asks at what time is the particle at rest, and that just means I want my velocity to equal 0. So I take my velocity equation from part A and I set it equal to 0. And I set it equal to 0, and when I solve by factoring, I get 2 times that give me a velocity of 0. On the last 2 questions, I'm asked for intervals where the particle is moving to the right or moving to the left. And I know a rightward movement is when velocity is positive, and a leftward movement is when velocity is negative. So to do this without a graph, I'm going to do what's called a sign chart. And this is for velocity. And I know values where my velocity equals 0. It's the 1 and the 3. So I'm going to put those on my sign chart. And I'm doing the sign chart for velocity because it's velocity that I need to know the sign of, which in turn will tell me these intervals where my particle is moving right and moving left. So the idea is to pick a number on each of these intervals. So I'm going to pick a number that's less than 1. and I'm going to plug it into my velocity and see if I get a positive or negative on that interval. So when I plug a number less than 1 into this first factor right here, I would get a negative number. So if, say, I get a 1/2 minus 3 is a negative. When I plug it in here and subtract 1, I get a negative. And when I multiply two negatives together, I'm going to get a positive. I wrote a little note here on the side. We don't really need to know what the actual value of that velocity is. All we really care about is if it's positive or negative. So I didn't deal with the actual numbers, just the signs, just a little sign analysis. So I'm going to pick a number in between 1 and 3, like a 2, and I'm going to go to this factored form of the velocity equation. And when I put a 2 into this first factor and subtract 3, I get a negative. And when I take a 2 and I put it into this second factor and subtract 1, I get a positive. And when I multiply a negative times a positive, I get a negative result. And then one more interval to try. My t is greater than 3. And when I put numbers greater than 3 into each of these factors, they're both positive. And when I multiply two positives, I get a positive. So I just found what the velocity is, the sign of the velocity for each of these intervals. So wherever my velocity is positive, which is on this region up until 1 and then after 3, I know my particle's moving to the right. And where my velocity is negative, which is in between the 1 and the 3, I know that indicates a leftward movement. And when you're using sign charts, make sure you realize they are not standalone evidence. You have to take the information the sign chart is telling you and summarize it in a little statement like I've done right here.